All right, thanks for the introduction. And first of all, thank you for the invitation, Marcus. I'm very happy to be here. And welcome to my guest lecture on pen testing iOS apps with a special focus on runtime analysis and manipulation. If you have any questions, I'll be glad to answer them at the end of my presentation. And before we start, I have a few words about me on the next slide. I'm currently writing my PhD thesis at the Security Research Group of at the University of Erlangen-Nuremberg. So the main focus of my research is based on the security and privacy of mobile applications. So for example, we are currently researching new techniques on automated dynamic analysis to conduct empirical studies on the security and privacy landscape of mobile applications. Beside my academic work, I'm co-founder of NISO Security Labs, a security research and consulting company based in Heilbronn. We are specialized on software security and do a lot of penetration testing, code analysis of different kinds of software, from native software to web applications, and a lot of mobile applications in the last years. I'd like to begin this talk with a word on the current state of mobile application security. When it comes to a mobile app assessment, most of the time is spent looking for vulnerabilities in the back-end web services. Those of you who have ever conducted an assessment of a mobile app might agree on that, and there are many reasons for that, and just to name a few, most apps are communicating via HTTP to back-end web service. And so it's quite easy to adopt all well-known methodologies from a browser-based world to assess the security of a mobile app's back-end component. In addition, we have plenty of tools and scanners for revealing vulnerabilities in web applications, and we could just go on using them in order to spot vulnerabilities in web applications or web service backends like SQL injection, directory traversal, and all that stuff. Compared to that, there's so far only little information on mobile app assessments, and to make matters worse, we have almost no tools to assist assessments of mobile front ends. So the purpose of this presentation is to enlarge that mobile app slice and to attach more importance on the app itself. And I promise you it's worth it. During the last years, we are observing a strong increase of client-side security measures inside mobile apps. One popular example is the WhatsApp messenger, in which I found some serious security vulnerabilities almost 2 years ago. Exploitation of these vulnerabilities allowed an attacker, a remote attacker, to take over any WhatsApp user account and to read messages and to send messages on the account's behalf. And remote means not only the same broadcast domain or sniffing in the wireless, but the same internet. And the reason for that was a flaw in the registration process of WhatsApp. So the verification of the mobile phone number actually only happened inside the app itself. So it's worth to look behind the scenes, and that's the motivation for this talk. To share all the relevant knowledge on app assessments we gained through the last years, I'm going to divide this presentation into 2 parts. At the beginning, I'd like to give you a broad outline on the Objective-C runtime. I will show you how running iOS applications can be extended with additional debugging and runtime tracing capabilities, and how this will facilitate both static and dynamic analysis of iOS apps. After that introduction, we will focus on different use cases and impacts. So if you are going to be a pen tester after graduation, you should be able to explore the attack surface of an iOS app more efficiently. If you become a developer, you might prefer to avoid client-side logic or at least security measures inside apps. And if you should straightly enter business as a decision maker, you should be aware of the emerging risks. Just a few comments on what this talk will not cover. So we won't look on at security vulnerabilities in the underlying operating system. So probably Stefan Esser will give you more insights on that. And we also won't discuss basic procedures of app pen tests, as there have been plenty of talks in the past. So you can look up those basic procedures like intercepting network communication, decrypting apps from the App Store, and so on in publications from the past. We're trying to go one step further and focus on manipulation and analysis at runtime level. Let's start with a quick introduction to the Objective-C runtime. So before we have a closer look at the runtime, let's talk on Objective-C for a moment. Objective-C was developed in the early 1980s, and it was the main language used for the next step operating system from which OS X and iOS have derived. Therefore, all iOS apps are written in Objective-C. Objective-C provides a set of extensions to the C programming language, which are mainly an object-oriented design, messaging concept based on message passing. We'll have a closer look at this in a second. We have a dynamic typing and reflection abilities, which is the ability of a program to modify its own behavior at runtime. You might know this from Java, for example, those reflection abilities. They're also available in the Objective-C runtime. And all these concepts make Objective-C quite attractive from a hacking perspective, and this is what we're going to look at now. Let's start with some sample code in Objective-C. So we have a Hello World class which is allocated and initialized, and the method sayHello is called, and this method simply prints out the arguments, as you might have guessed. We'll come back to that sample code in a second. In the meantime, we'll have a look at the actual runtime. As apps are executed natively on iOS devices, what makes the runtime? During the build process of an app, all apps are linked to the so-called libObjective-C dynamic library. And you could extract information on all linked libraries from an app binary using the object file displaying tool from Apple. And you will notice that every iOS app is linked against this library. And this library provides all runtime functionalities of the Objective-C runtime. So this makes the runtime. And one of the probably most important functions of this runtime is the function Objective-C message send. It serves as a central dispatcher for that message passing concept. So this runtime function is used to send messages to existing objects in order to invoke a specific object method. It's like calling a function in C. And this dispatcher function accepts at a minimum 2 parameters. So the first parameter is a pointer to an instance of the class whose method we want to call. This is called the receiver or the receiving object of that message. In our sample, this is an instance of the Hello World class. The second argument to the dispatcher is the name of the method that should be invoked. In Objective-C, this is called the selector. In our sample, the sayHello method. And in the end, the dispatcher receives a variable list of arguments which is sent to the sayHello method. So please keep in mind that every method invocation in Objective-C results in one or more messages to that central dispatcher. That's going to be important in a few seconds. Let's talk about how this runtime behavior influences security assessments of mobile apps. As in any kind of software security assessments, two different approaches do exist: static and dynamic analysis. While static analysis gives you detailed insights into a mobile app and is of course the preferred way of performing a security assessment, it's not always the most practicable way. Imagine when there's, for example, no source code available and you have to do the static analysis on a disassembly. or when you have a look at the disassembly, you might notice that the characteristics of the Objective-C runtime makes it difficult to follow the control flow because of that dynamic messaging concept. In the end, static analysis is quite time-consuming, and as a pen tester, you're always on a tight deadline, need to finish the report and so on, so you don't have much time during a penetration test. So what can we do? The good thing is that the characteristics of the Objective-C runtime enables comprehensive dynamic analysis. So I put this on the slide. You could, for example, intercept all those messages to the central dispatcher to get a complete trace of the internal control flow and see all method invocations. That's the first thing. Or you could even send arbitrary messages to existing objects. If you know the location of the object in memory and you know the method you want to call, you could just send your own message to the dispatcher. Or you could rewrite the whole implementation of arbitrary existing methods due to the reflection abilities. And then you really start to manipulate the internal state and the whole processing logic of an iOS app. And this is what we're going to look now. So keep in mind that it's worthwhile to always combine both static and dynamic analysis to evaluate an app's security level in an economic, reasonable time frame. It's very efficient, what we'll see in a second. So that's it for the introduction. Now let's move on and have a look at some backgrounds and techniques to interact with that runtime and to manipulate iOS apps at runtime. So our goal right now is to perform a black box analysis of an arbitrary iOS app. Black box means we have no source code available, only the app binary, which could be an in-house developed enterprise app or an app from the official app store or even from the Cydia store. The typical approach which is chosen for mobile app assessments is to examine the app on a jailbroken device. This has many advantages. So first of all, the jailbreak removes all the limitations imposed by Apple. It provides you with root access to the operating system, to the iOS operating system. It enables you to install additional software like debuggers and analysis tools. And it gives you comprehensive access to this Objective-C runtime and to interact with it. As we heard before, the Objective-C runtime offers a wide range of different opportunities to manipulate existing apps. So you could replace whole method implementations. We'll see that soon. But before we start to manipulate what happens inside an app, we need to extend the app code with additional code. For this, two different approaches have proven to be extremely practical. So we could either inject a static library with new functionalities, or we could inject an interpreter for on-the-fly manipulations. And we'll have a look on both of this, and we'll start with the static library approach. To inject additional code in form of a debugging library, we make use of the environment variable insert libraries. This variable advises the dynamic linker, which is a component of the operating system, to load an additional dynamic shared library into the iOS app address space at startup. It can be compared to LD preload under Linux. And during initialization, our debugging library needs to reroute the program control using runtime patching techniques. So in the case of Objective-C, the implementation of an arbitrary method is replaced at runtime using reflection functionalities. In the case of a C function, we need to do something like detour runtime patching and pointers whistling to redirect the execution to our own library implementation. Let's take an example. In this example, we have the original iOS app, we have an API method, an iOS framework, and we have our own library, the replacement. And let's say our app wants to look up the unique device ID. For this, the app invokes the related API method, and Using runtime patching, we redirect execution flow at the beginning of the framework implementation to our own implementation and redirect it to our library code. From within the library code, we could call the original code if we wanted to get the original value of the device ID in this example. It will return back to our library, so we could also inspect that value or modify it. And in the end, we could return any value we want back to the application. So we are in the middle of the execution flow and intercept every method call to the iOS API. In practice, I'd highly recommend you to use the mobile substrate framework. Mobile substrate consists of two parts, a mobile loader and a mobile hooker. The mobile loader will first load itself into the application using the environment variable, and then it looks for all dynamic libraries in a specific folder and loads them via DL open into the app's address space. And the mobile hooker does the actual hooking. So the function msHookMessage will replace Objective-C method implementations, and msHook function is the same like msHookMessage but for C or C++ functions. And to ease the development of such libraries, which are called tweaks in the iOS world, I recommend you to use the Theos development suite in the references to set up your build environment. So here's an example of a first tweak. When that library is loaded, the implementation of the method unique identifier, which will return you the unique device ID before iOS 7, whenever the class UIDevice receives the message unique identifier, it will return this value, that implementation, and that implementation will always return a static string. That was the first example of a simple tweak. That was the first way of extending apps with additional code using injected libraries. Another, even more flexible approach is to inject a whole interpreter into an app. This enables spontaneous, on-the-fly manipulations at runtime. Let's have a look at Script. Script is a programming language designed to blend the barrier between Objective-C and JavaScript, developed by Jay Freeman. When using Script, a JavaScript interpreter is injected into a running app based on the mobile substrate framework, and this enables runtime manipulations in a very flexible way. Let me show you one example to make it more clear. One of the most powerful features of Script is the ability to attach to an existing process. This is not an attach on a debugger level, but on a runtime level. This gives you access to all classes, instances, methods, and variables at runtime. You could invoke arbitrary methods or even replace the implementations. So after attaching to a sample app, you could execute any Objective-C method or even JavaScript inside this interpreter. This will execute it. And with Script, you don't need to set up a build environment, compile your library, transfer that library to a device. So it's a very flexible approach. You could even replace implementations of API methods. So this is the example which I shown you earlier on the static library, just transferred to Script. Every time that UIDevice class receives a message to call unique identifier method, it will return ROB. These modifications are specific to the only app in scope. A library can be used to intercept flows within more than one app at the same time. And then querying the unique device ID again, and this app will assume it is ROB. This is the app I demonstrate from the Apple App Store, just to demonstrate you that it really works. And this shows you the result of our runtime modifications. So I'm willing to own that this is not rocket science to replace a value of a unique device identifier, but it demonstrates the diverse possibilities of runtime manipulations. During the last years, I had several phone calls from friends within the pen testing community, and they asked me if it would be possible just to fake those identifiers, and I showed them those basic techniques. And so the app under review, which they were assessing, the security model of that app could be completely broken because it relies on hardware identifiers for authentication. And this is very often the case. Don't forget that only 2 years ago, WhatsApp was using the device identifier as a login password. After I told them that this is not a good idea, they switched over to the wireless MAC address. It's quite questionable if this was a better approach. Or imagine when you have a mobile app which uses a binary or web service protocol, like Google Protobuf or any binary web service protocol. In the end, you don't have to reverse engineer the protocol. You could just modify some values at the application endpoint and get your SQL injection payload, for example, packed and transferred to the backend web service from within the app address space. So those manipulations are often very time-saving. Let's look at some more use cases. As we have seen, running apps can be extended with additional debugging and tracing, runtime tracing capabilities. This is a great feature to assist security assessments of mobile apps. Runtime manipulation makes it a lot easier for us to discover vulnerabilities inside apps. I will show you that in a few minutes. And even to prove client-side security measures useless. In the following, just one example, and more will follow soon. When it comes to evaluate the encryption scheme of an app, a typical question is which app methods are called after the user passcode was entered. This is a typical question. And to answer that, we could make use of dynamic analysis to reconstruct the control flow, to intercept all those messages, and to use the results to navigate through the static code. To get a complete trace of all methods which are called, we could log all messages to that central dispatcher function, to that Objective-C message sent. Let's have a look at the GDB way first. So after attaching to the app process, we could set a breakpoint in the Objective-C message send method. And every time that breakpoint is reached, we print out the CPU registers R0 and R1. R0 is the first argument to that function, which is the receiving instance, and we resolve the class name of it. And R1 is the method that should be called. So when we start looking at the output of such an approach, we recognize very fast that this approach makes an awful lot of noise, because all background activities of the iOS operating system and all touch events generates hundreds and thousands of those method invocations in the background. So it's really unrewarding since it's very hard to figure out app-specific calls only on a debugger level. A better approach would be to intercept those messages on a runtime level within the runtime. So when we hook the Objective-C message send function on a runtime level, we could apply different filters. So using the runtime first, we enumerate all registered app classes and methods which are available in the app binary itself. Then we intercept all those messages to that central dispatcher, and we only print out those matching items which are also available in the application binary. And this gives you a complete, clear trace of app method-specific invocations. The tricky part is to handle all parameters and to continue normal execution, as we are intercepting in a very sensitive part when a message should be passed to an object. And it's very important to keep the CPU registers, and logging itself would modify the CPU registers again. So the solution for this is to preserve the current execution state. We allocated some alternate stack within heap memory and back up all the important register from R0 to R3 and the link register to an alternate stack. Then we could use the CPU to do all the logging and filtering activities. And after logging, we just had to restore the original CPU registers and we could continue execution. Doing so, no arguments will be lost, although we intercept in a very sensitive point. And this is a sample output of a password-safe app, so secret password-safe app from the Apple App Store. It shows the trace of app methods after a user has entered his own passcode. What we can see very quickly is that only a constant string is used for decryption and not the actual user passcode that was entered. So this is bad crypto, but I call your attention to that key derivation function. At least the developers try to derive a strong cryptographic key out of a constant string. So quite questionable, but however, hopefully that constant string was guaranteed to be random. So within seconds, we have evaluated the encryption scheme of a password-safe app from the App Store, which we only have in binary form and no source code available, without the need for doing any static analysis at all, just through dynamic analysis. As you can see, runtime analysis can be very, very time-saving during a penetration test. That was just one example on how runtime manipulation assists security assessments. Imagine apps where there's a light version and a pro version. Often the light version contains the same code from the very beginning, but the pro features are simply not accessible from the user interface. So now you know how to upgrade your light version. Or imagine in-app purchases. Most of them are broken by design. As newly purchased features already reside in the original app code from the very beginning. You just need to figure out the method which activates your in-app purchase. It also gets very interesting when apps deal with copyright protected content like movies or newspaper articles. All those data is accessible at runtime, like movie streams or newspaper articles, and can be dumped easily using those runtime techniques. To sum up, runtime manipulation is a great feature, can be very time-saving, and it also increases the attack surface of a mobile app. So it assists security assessments. New attack vectors arise. The problem is that there are almost no tools available for dynamic analysis of iOS apps beside those techniques I showed you. And as Josh Wright said, security will not get better until tools for practical exploration of the attack surface are made available. And in the following, we will close that gap. During the last years, we have developed several tweaks for different use cases in penetration tests. And it was quite time-consuming to maintain all these tweaks and to keep an overview. That was the reason why we consolidated all these little helpers into a comprehensive debugging library. And to make all the functions in that library accessible, we extended it with an XML RPC web service endpoint. And we also started a web server inside the iOS application. And this web server provides you with an HTML JavaScript web frontend based on Google Web Toolkit, and it communicates with the library via XML RPC. So a tool for practical exploration of the attack surface of a black box iOS app. That idea was the birth of Snoopit, a tool to assist security assessments and dynamic analysis with an easy-to-use graphical user interface. Let's look at some features. We could monitor all the file system access and all the syscalls which are used for accessing files on the file system. And we also print out all these data protection classes which can be used to encrypt files using the iOS encryption mechanisms. So this is very useful to spot, for example, files that use or don't use Apple file data protection. And from now on, it takes you only seconds to spot configuration files that store sensitive data in clear, for example. That's a typical use case. We monitor all access to the keychain, all HTTP, HTTPS connections, access to sensitive API, like the address book when an app accesses your photos or your camera or your location, your clipboard, access to the microphone. It takes you only a few lines of code to switch on the microphone in an iOS app and to transfer the recording to a server. And that wasn't restricted on an iOS device before iOS 7. So every app could do that. And we could spot those privacy leaks. We also put on the very powerful tracing feature to trace internal app method invocations. We could fake hardware identifiers. If your app relies on a static hardware identifier like a unique device ID or wireless MAC address, you could fake it from the web interface. We could modify location data. Quick story on that. I had to assess an app which was supposed to only work on the company grounds. So a typical client-side security measure. I had two choices. Either I could travel abroad, stay in a hotel again, or I could find a way to spoof location data to the app and sleep at home. So you could guess which option I had chosen, and the result is also integrated in here. So we'll show you this in a second. We could list URL schemes. We could list all available classes in an app binary, invoke arbitrary methods at runtime. And we tried hard to make Snoopit as easy to use as possible. So you can grab our package, install it. You will get a configuration app and that library providing the web server. So quite easy to use and to set up. We also provide a complete documentation of the web service interface. So there's no need to use our web-based interface. You could just use our library within automated analysis within a Python script, for example. And it's freely available from project side. After installing our package, you will find a configuration app. You just have to open it, select the app you want to analyze, adjust some settings like the web server listening port, and then fire on your app and point your browser to your device IP. And I will show you this right now. So what you can see here is the Snoopit configuration app icon. I will open it. And it provides you with an interface to select the apps to analyze. I already pre-selected some of the apps. Then you could adjust settings like the web server port, the tracing, the different tracing filters. We'll come back to that in a second. And I will start with that simple flashlight application. So during start, our library is injected using the insert libraries environment variable. A web server is running, and now I can connect to the web server, which resides inside the app. So nothing to set up on your client device. It all happens on the mobile device. And you can see that it was compiled with support for position-independent executable. We can see all the debugging outputs which were forgotten to remove by developers. And, for example, all the file system accesses, which are here restricted to the application sandbox. And we see a lot of different file system accesses to some interface files, some audio files. So nothing sensitive to expect in a flashlight app. With different filters, you could also monitor system-wide access to get all the background activities of iOS. And we also grab all the iOS encryption file data protection classes. So none of these files are encrypted with iOS mechanisms, as this protection class indicates. This is also shown by the red button here. If it's green, the iOS encryption scheme is used to protect these files. Access to the keychain, and the first interesting thing is all the captured network connections. Remind that this is a simple flashlight application to provide you with some light, and this shows a very typical behavior that even it's a flashlight app, it communicates to at least 4 different tracking and advertising services, which monitors you every time you open that app. It tracks your, let's take these from Tapjoy ads. So it sends data like my country code, my MAC address, my iOS version number, my provider, Deutsche Telekom, that I'm using an iPhone, my MAC address, my unique device ID, and also my device name. So if your iOS device is configured as your pre-name, last name's iPhone, you should change that value as it's transmitted to any advertising service which is prevalent in an iOS app. We also track access to sensitive API. A lot of Wi-Fi MAC address accesses due to these plenty of tracking services. They're using your wireless MAC to identify you. Access to the camera, which is just the LED which is switched on. This is in the camera component. Can fake hardware identifiers from here, or we could even pretend to be an iPod Touch or an iPad, and a fake location feature, which is only available when you are connected to the internet. As we display a Google map, you could just point a location and switch the feature on, and afterwards that app will think you are at that specific location. So quite easy to spoof location data. And thing which I want to show you is this. We have access to all the objects and classes and class methods from the app binary. We are enumerating all these values using the Objective-C runtime. Red dot means this is a class available inside the app binary, and green means that we also tracked an instance of that class. So during initialization, we track all these instances and store the location in memory just to invoke instance methods. We could click on the camera LED encode, for example, and we try to rebuild the Objective-C syntax. And we could choose the method open camera LED, for example, and could use that button setup and invoke. We just have to select the position of the to select an instance, and to invoke that method open camera LED will switch on the camera LED. This is a good example to show you that it really works to remotely control that app from the web service. Otherwise everything could have been fake, which I showed you right now. So I'll switch it off again, otherwise it will get hot. Forgot that in one of my last presentations. So let's do another use case, a real use case. This is quite useful to spot privacy violations of apps, for example, like all these advertising services, access to sensitive API. Now let's do another use case of that iPin Lite app. Is anyone of you using that password safe app, iPin? So no one dares. No? So let's look at the description first. This is the official description of iPin. It says the highlight is log in with the sensor keyboard. So with an innovative sensor keyboard, you'll have quick access to all your pins without any annoying and time-killing passwords. Sounds great. Sounds like a perfect example for when usability meets security. It's quite easy to use. Let's look at the security right now. Regarding security, it says in the description, security is of greatest importance. All data is encrypted with AES 256-bit, state-of-the-art encryption algorithm. Keep it simple and secure. So nothing could go wrong. Let's look at this app. So I will start it. No, first we'll go back to Snoopit and switch on that tracing feature to intercept all messages to Objective-C message send to see what happens inside the app. So after switching it on, I need to start the iPin Lite. Yeah, I need to restart it completely. The web server was already running. All right. So it fires up. We could refresh our session. This is a new app. And I will go to the File System tab first. Because what we see quickly is that the app does not make use of the iOS encryption schemes. So all data which are stored are in clear. And these are a lot of interface files, localization. There's the app binary itself. And there's one very interesting file access, which is an access to a file called ipin_security_model.dat, which resides in the library ipin data folder. So at best, all our sensitive data is stored in that file. We could just do a double click on that file to download it, so no need to SSH into your device. And have a look inside it. It's only binary data, encoded data, or maybe encrypted data, not clear about that. But we could make use of our tracing feature to see how that file is processed in the app, the iPin security model. For that, I open the method tracing. We see a trace of all the methods called. We could also call back to old log files or download the current log file. And now I will look for security model. Here it is. So init from file, the security model file path. This was the file which we saw a few seconds ago. And what we can see very quickly is that I had shown you in the slides that a key stretching is used on a constant string. So this is the constant string used for encrypting this file. Probably the developer just copy and pasted a method name and used this as a string which was hard-coded in the app binary. What is inside that iPin security model file? Inside is, so all the results of that file are stored in an instance of the class iPin model. And in the iPin model is stored a hash value of the sensor, a sensor hash. So we have here an innovative sensor keyboard. How does the app know if the entered code was correct? It stores a hash on the device, which is encrypted with a constant string and also stored on the device. So I will copy that sensor hash because we'll need this in a second, and a few other data. Now we'll go down because we are interested in what happens when I just press a single button here, the upper left one. Just press it, refresh, and I will see all the method invocations which were caused by that simple touch. We go down and look for this one, the last one. And what we can see here is that the sensor keyboard view controller, this is the name of that sensor keyboard, which takes all these touches, returns a value of 10 when the upper left button is pressed. When I press the upper middle button, it will return a value of 20, value of 30 on the upper right. So it's enumerated from 10 to 90, all these values. And after value of 10 is returned, it will calculate an MD5 hash, an MD5 value of this value of 10. So if I press another button, let's do it like this. So I've pressed these two buttons, we'll refresh it again. We will see that those two values are concatenated and an MD5 value is calculated, and this is compared to the sensor hash, which was stored encrypted with the constant string on the device itself. So the attack is quite simple. We could just brute force all possible combinations from 10, 10, 10, 10, 10 to 90, 90, 90 until we derive that hash value which we copied earlier. And for this, I wrote a small Python script, give it the sensor hash, which we derived from that file. And in less than a second, we get the actual sensor code, which is required to unlock the device. It's 10, 20, 30, 60, 90. So within seconds, we spotted a few mistakes in the app implementation without the need for any static analysis. We don't have the source code, just an app from the App Store, and quite easy to spot those implementation flaws. Let's go back. So Snoopit is freely available on the Google Code project site. You could use Google to find it. So if you have any old iOS device like an iPod Touch or an iPhone 4 or anything, just jailbreak it, use it, and have a look at those security flaws in mobile apps. There are plenty of to get revealed. So during the last weeks, we got a lot of positive feedback. Snoopit is used by pen testers all around the world in the meantime. I put in one feedback on this slide. Arjun said, I'm totally impressed by the way Snoopit has eased down on assisting iOS apps. I managed to identify flaws on client-side implementation in no time. The method tracing feature is a blessing. Even several companies are using Snoopit to review apps from the App Store for privacy violations, if an app accesses contacts or the microphone and so on, before whitelisting apps and allowing them for company internal use. Another use case. This summer we published a study on the security of mobile hotspots, the iOS personal hotspot, where you can use the internet features of your mobile device when it's tethered to your computer. Using these dynamic analysis techniques I showed you, we analyzed the official preferences app from the iOS operating system, and we found out that on a first spot, default passwords of the hotspot functionality consists of only 4 to 6 characters followed by a 4-digit number. So these was the default passwords for the hotspots, and this alone would enable brute force attacks on a captured WPA handshake, but it would take too long. In more detail, we observed that in fact the iOS spell checking framework was used to suggest a default password after installation. So this framework is usually used to underline misspelled words, and Apple reused that functionality to suggest you a default password. This is why default passwords are derived from an English language dictionary. The problem is that we found out that only around 1,800 words of that dictionary are used for default passwords. And compared to the number of millions of sold iOS devices, 1,800 different passwords is quite limited, right? And in addition, even the process of selecting words from that limited dictionary was not random. So words from the top 10 are 10 times more likely to be used as a default password than any other word of that limited 1,800 list. So these two flaws gave us the possibility to compromise a hotspot connection in less than 50 seconds using graphics processing units after capturing a WPA handshake. So these have been the most frequent hotspot passwords in the wild. And for more information, refer to our JS website. This serves as a perfect example why it's always a good advice to replace default initial passwords by user-defined strong passwords. By the way, we notified Apple about this flaw, and this was fixed in iOS 7. Within iOS 7, it looks like this right now. It looks quite more random than before. This is another use case of dynamic analysis, which we used just to retrieve those results. One more and last thing. More and more apps perform some kind of jailbreak detection to verify the platform integrity. So mainly banking apps or movie apps or apps of mobile device management solutions used in enterprise try to detect if they were executed on a jailbroken device. For that, they perform common checks like looking for suspicious files and directories, traces of public jailbreaks, like an application Cydia app or an SSH daemon. It looks for file system permissions, if the root partition is writable or not. Looks for some mount options, as during a jailbreak, all the applications are moved to the user partition as there's more space, and a symlink is generated from the root partition to the user partition. So one typical check is to look for those symbolic links. Looks for dynamic shared libraries. Some do kind of SSH loopback and try to spot an SSH daemon running on the device, sandbox integrity checks, and all that on. The problem with these checks is that all of them rely on information provided by an untrustworthy runtime to determine its integrity. So this could never work, and it's almost the same as you would try to detect a rootkit on a host operating system from within a virtual machine. So this is what a jailbreak check looks in static analysis. It's quite small, but you can spot here the applications folder string. With that else.syscall, it's looked if this applications folder resides in the root partition or is a symbolic link. Then you see them access to the file system table, where it is checked if the root partition is read-only or read-writable. So these are typical jailbreak detection patterns. Since we are testing apps on jailbroken devices, we need to bypass those checks to begin our assessment. For this, we could either patch an app binary offline or at runtime. So one of the most basic checks and one of the most simple checks to bypass are Objective-C methods like this. So you can spot this very often in apps. There's a method which is called isJailbroken. It returns yes on a jailbroken device and no on a non-jailbroken device. To bypass this, you could just use script, and that every time your instance receives this method, just return no. It's the simplest bypass of a jailbreak mechanism. A more generic way is to intercept all system calls and to simulate an unmodified execution environment. This is more generic. For example, we are already intercepting all system calls to the file system accesses. Then if a suspicious file system is tried to access, we simply return no in that cases. The good thing is that Snoopy already supports bypassing of most of the common jailbreak detection mechanisms available. For this, we hook all those major system calls and pretend an unmodified execution environment. And to activate that bypass, you just have to switch it on inside the configuration app. And I will show you this in the last demonstration. I chose the app 3D Central. I have no clue what this app is for and what it does, but it performs a jailbreak detection. And this is enough for that demonstration. So you see that it says jailbroken device are not supported, and you can't use that app any longer. So I will close it and just configure Snoopy to bypass that jailbreak detection. Now we will hook all system calls and pretend as good as we can an unmodified execution environment. Now we'll restart it again. And as you will see, the jailbreak is not detected any longer. So don't rely too much on those jailbreak detection features and mechanisms. It's quite easy to bypass them. So this is a quite useful feature in Snoopy to not wasting too much time during a penetration test on disabling the jailbreak checks. Recently, we examined the jailbreak detection mechanisms of Mobile Iron and Good for Enterprise, which are popular app containers and mobile device management solutions in enterprises. And we broke all of these detection mechanisms within a single day. So don't rely too much on those. How could one do it better? Is the question. So we researched techniques for some advanced jailbreak detection to be integrated into iOS apps and developed AppMinder. AppMinder is not written in C and not written in Objective-C, as this can easily be bypassed. So we wrote it in ARM assembly and put in various code obfuscation techniques, self-integrity checks, anti-debugging measures. So if you're an app developer, you could just use our web service to copy your own polymorphic jailbreak detection code written in ARM and put it inside your iOS app. It's a free web service available. And don't get me wrong, of course, all those AppMinder checks can be bypassed as well. But we just try to raise the bar very high. Obviously, the best thing would be to entirely avoid the need for jailbreak detection at all. But if you need to, you could grab our web service, and please expect an updated version of AppMinder with optimized obfuscation within the next few weeks. So to conclude, I'd like to discuss some countermeasures for securing the runtime when you are developing an app. The first and very most important commandment is keep only a minimum of data and logic on the client side inside the app. And at least no client-side security measures, as all of them can be spotted very quickly, as you have seen in the demonstration, and can be bypassed very easily. I recommend you to prefer the use of C instead of Objective-C, at least for security-critical implementations. So you have inline functions which could be used, and more possibilities for obfuscation. Try some advanced jailbreak detection if you need to in runtime integrity checks. At least try to, it's worth a shot. And well, what I want you to take home is that runtime analysis and manipulation facilitates both dynamic and static dynamic analysis. Keep all those demonstrations in mind, how easy it is to spot static strings when they are used for encryption, for example. The attack surface of iOS apps can be explored more efficiently, even with our new tool Snoopit, which is freely available. So for you future iOS app assessments, that means when in doubt, just snoop it out. Thank you very much for coming.